Hi everyone, today we're going to be talking about the transmission through a diffraction grating used to determine the wavelength of light. This is something that they use in analyzing starlight, so this is why we're introducing it here, and it's something that you have already used in an experiment we've done with the laser beam and the diffraction grating, but we'll get to that later. You will also need to know the condition for maxima that's linked to this equation. We'll explain how it's derived as well, even though you don't need the proof for this equation. We will look at Wien's displacement law, which has to do with the wavelength and maximum temperature of a star. We'll also look at the luminosity of a star, how it's linked to the temperature of a star and Stefan's constant. And we will be able to use a combination of both Wien's displacement law and Stefan's law to find the radius of a star, since it's involved in one of these two equations. So this is lesson 3 for the stars, chapter 19. So let's firstly start with what is a diffraction grating. Now, diffraction grating is simply an optical component, so it's this what you see in the picture, that has regularly spaced slits or lines, we call them lines as well, that will diffract, so spread the light out, just to remind you. So there's a lot of them, and when they diffract, they'll split light into beams of different colors. So if it's white light, as it spreads it out, we know that white light is composed of the rainbow colors, so it will split the light into beams of different color, and they will be traveling in different directions. So basically, a diffraction grating just simply has a lot of slits that diffract light. Now, what you see in the picture are different diffraction gratings, and there's something that's popping up a lot on them. So this states how many lines or slits are in each millimeter, so per millimeter. We also know that for something to diffract, this is a quick reminder, by the way, we know that since diffraction is the spreading of waves, and we also know that in that case, for a wave to be able to spread or diffract appropriately, the gap size needs to be similar to the wavelength of the wave. So if we're talking about light, then we know light has a range of 400 to 700 nanometers roughly of wavelengths. So we need something similar to that. We need the gaps to be similar to that. We have seen in year 12 the experiment for the double slit experiment. We analyzed how that will work. In this case, we have more than just 2 slits. We have loads of slits. So what's the difference in the fringes produced by light passing through a double slit rather than a diffraction grating? Well, the double slit actually produces fringes that are not very sharp. So remember that if you pass light through a diffraction grating or even a double slit, so this was the double slit, if light passes through that, the slits actually act as two coherent sources, which allows the wave, so if we're talking about the wave fronts or even the ray beams, they will spread out from those two sources. Now, if you have more than that, obviously you will have a clearer and better interference pattern created. So you will have clear fringes, so bright and dark fringes, which will help you determine easily in terms of the diffraction grating, the pattern, and therefore the center of each maximum. Because we did do this experiment, we did take the center of each maximum and we used it. So what does it do? We already said, if you have, for example, monochromatic light incident at a diffraction grating, it gets diffracted at each slit. The diffracted waves will superpose and will create an interference pattern. So the interference pattern, to remind you very quickly, it forms maxima and minima, where maxima in terms of monochromatic light, meaning just one color light, it forms maxima where you have bright fringes, so the brightest color, and it forms minima which means that it will have no color at all. It will be dark, basically, fringes where the waves cancel out. Now this depends on the path difference and phase difference of the waves. So something that we will be looking at later. Now this shows you how if you pass white light through a diffraction grating, since each wave will diffract, well, each part of the white color will diffract, and it's got all the different colors of the rainbow, you can see that red diffracts much more than the violet color. And that's because red has a bigger wavelength than the a violet color. And also you can see that since it diffracts it, the different colors split, and you have an interference pattern with multiple rainbows splitting at each point. However, the central maxima is actually white because they don't split in that way. They have a zero phase difference at the center, and zero path difference compared to the other waves later on the other orders of diffraction. Okay, so a very quick reminder that light is a transverse wave. Also, wavefronts is basically lines that join the points that are in phase with each other. I thought it would be a good reminder, and since the 2 points are joining points that are in phase, we know that this is a whole wavelength, so the distance between them should be a complete wavelength. So zero order is formed when the path difference between the waves arriving at that point is zero. So the first order, the zero order maxima that's formed in the center has a zero angle from the normal. This is the normal. Oops. 1 second. So this is the normal lines that we're talking about, and this is the angle theta that we talk about too. So I'm just going to remove that so I can work with the diagram. So the first order maxima, however, will have a path difference of lambda, and I'll show you how that works on the diagram. So here we have the wavefronts, so these blue lines here are wavefronts, and these are like the rays of the wavefronts. Now we can use that to compare how much further one of the waves from A is compared to the wave coming from, so the wave from A compared to the wave coming from B at that point. And this green line is drawn to basically show that. Now, wave A and wave B have a path difference. And since that path difference is equal to the whole wavefront, then the path difference is equal to a wavelength. So what I can do is draw a triangle and use that to do calculations. Now this is a right angle triangle. What you have is this, the right angle triangle. Since we said that this angle here is theta, this one is also theta. It works out if you do the similar triangle, since you have this triangle here and so on. So if you shift that, that will be the same angle as it will be there. Sorry, this looks a bit weird. So this angle theta if I shift and rotate this triangle, so if I take it, so right now it looks like this. This is theta, this is the right angle. If I rotate it clockwise, well, kind of clockwise, it will make a bit more sense if you rotated, yeah, that way. But yeah, they are similar triangles. So this will be your angle theta 1 that we're interested in. And we know that this distance here between A and B is the distance between the slits. We're going to come to it in a second though, so just for the mathematical reasons here. By the way, you don't need to know this proof, it's just if you're interested in it. So that distance A to B is D, and the distance here to here is equal to 1 wavelength. So we can use trigonometry, so that will be opposite over hypotenuse, which is sine theta. So sine theta is equal to lambda, the wavelength, over the distance between the slits. Okay, so that leaves us with lambda is equal to d sine theta. However, this is just for the first order diffraction. If I consider the second order diffraction, then I can see that the wave coming from slit A is 2 wavelengths away from the the wave coming from B is 2 wavelengths ahead of A. It has a path difference of 2 lambda. If I take the triangle again, this is 2 lambda. This is the grating spacing. So D is for grating spacing. Lambda is for the wavelength of the actual wave. And theta is the angle from the normal of the diffraction grating to the rays that are coming out of it. So that will be, again, sine theta is equal to 2 lambda over the diffraction, the grating spacing. So you can see that if I keep doing that for every order, it will always be an integer multiple of the wavelength. So the general equation is this. So d sine theta is equal to n lambda, where n stands for the order of diffraction. D stands for the slit spacing or grating spacing in meters. Theta is the angle between the 0 and nth order fringes in radians. So these are the each quantity what it stands for. So n doesn't have a unit. Wavelength of light has a unit in meters. Grating spacing is in meters, and the angle could be in either degrees or radians. So how can I get the value of the grating spacing or slit spacing? Now this one is quite simple if you understand exactly what is going on here. Now usually, like I showed you at the beginning of the video, it tells you the number of lines per millimeter. It tells you not lines per millimeter like this. So that means there's 600 lines in each millimeter. So what I want to do first is turn that into lines per meter, since we need to know we need it in meters, the grating spacing. And to do that is simply 600 divided by 1 millimeter, which means 600 divided by 1 times 10 to the minus 3 meters. This means that you have about 600,000, if you put that in the calculator, lines in 1 meter. And then to get the spacing between each slit, you do 1 over the 600,000 lines per meter. So in other words, you just flip it over. So that's how you get the grating spacing from lines per millimeter. One more last thing on this is how you can get the largest possible order number n that you can observe. So when you do an experiment, usually you'll get the clear pattern of bright fringes, and you need to know how many those could be from your experiment. The only way to figure that out is using the actual equation for it. We usually call this the grating equation. And the only time that you can get the highest number of orders is when theta is at 90 degrees. Below that, so sine 90 is equal to 1. That's the maximum number. Just to remind you that sine is it's got its own wave, with the maximum being 1 and minus 1. So in other words, for you to be able to get the maximum number of orders that you can observe, you need to turn theta into 90. So that will mean sine 90 is equal to 1. Therefore, this will give you the maximum number of waves that you can see in that case. And also, just to remind you, the largest number of maxima should always be rounded down. Because, for example, if you get 5.65, you can't have 0.65 order, so it should be turned into 5 orders. And that's on either side of the central maxima. Okay, so just a quick example question. You have monochromatic light from a laser has this wavelength. So we're given the wavelength, which we need to change into meters. It's incident normally at a diffraction grating. The angle between the second order, so n is equal to 2, and the 0 order maximum is measured to be this much. So that's your theta. Calculate the grating spacing d. So you know that n lambda is equal to d sine theta, which means that you need to calculate d, so you will rearrange for d. And you just place the numbers in. And you should get 2 times 10 to the minus 6 meters. So that's the grating spacing. Now, if you want to know how many lines per meter or per millimeter, you just do 1 over this value. Even though I didn't ask for it, then you know how to do it. It's the reverse of each one. So why were we interested in this in terms of stars? Well, the topic involved splitting white light coming from stars, and how we identify the missing lines in that spectrum by splitting light through a diffraction grating. So this is closely linked to the previous lesson where we looked at spectral lines. So coming back to the outcomes, the transmission diffraction grating used to determine wavelengths of light, we've looked at it. We also looked at the condition for maxima coming from a diffraction grating, so how you can calculate how many maxima form by rearranging for n, or if you want to find the diffraction spacing, grating spacing, and so on. And we're going to have a look now at Wien's displacement law and Stefan's law as well. Also here, even though you don't need the proof of this equation, and you do need to know how to do the practical, which we have done already. Just a quick note here about the equation. When you are doing the experiment, you will need to be able to record what number order you're looking at, the angle theta, and then you can plot a graph of sine theta versus n. This will give you a straight line since sine theta is equal to n lambda over d. So if I compare this to the equation of a straight line, y is equal to mx plus c, it should mean that since there is no plus or minus value, there is no y-intercept, so it means it starts at the origin. Sine theta is your y quantity, n is your x quantity, which means that your gradient, which is a positive line going through the origin, should be lambda over d. And you will know d because you will be using the diffraction grating, therefore you can find the wavelength of the light that you were investigating by plotting a graph. Now we're going to have a look at Wien's displacement law and Stefan's law. These are linked to how the temperature of a star affects the way the color looks like. So if you have like really hot stars, they will look blue-white, and if you have cooler stars, they will look reddish. So first, before we move on to Wien's and Stefan's laws, we're going to look at what blackbody is. You need to know what a blackbody is. It's basically an idealized object that will absorb all the electromagnetic radiation that will shine on it. But when it's in thermal equilibrium, it will emit a characteristic distribution of wavelengths at a specific temperature. So it will look like something that you see in the graph here, with the intensity versus the wavelength of radiation emitted. So you can only see the visible part of the spectrum emitted by a black body. And we usually can model every object, including stars and metals and even animals, to be an approximate black body, because it really helps determine the temperatures of the objects simply by looking at the electromagnetic radiation that they emit. So this is something that we will be using in terms of how, for example, the temperature of the surface of a star is compared to its radiation, electromagnetic radiation that it emits. Now, every object that is above absolute zero, so 0 Kelvin, usually has heat, so it will be emitting infrared radiation and so on. Okay, so Wien's law. Now, Wien's law is quite simple. He relates the absolute temperature, T, so the absolute temperature means in Kelvin, of a black body to the peak wavelength, so to the maximum wavelength at which the intensity is maximum. So you see the same graph here with the intensity versus the wavelength at different temperatures. So you can see that as the temperature increases, the peak wavelength, that's the maximum wavelength of the specific temperature, shifts to a lower value. And basically, Wien's displacement law states that the hotter the object of the body, the shorter the peak wavelength of the curve will be. So in other words, L max is times the temperature is equal to a constant. Or otherwise, constant, temperature is equal to constant divided by the wavelength maximum. So as the temperature increases, the maximum wavelength at the peak intensity decreases. And this constant is equal to, this is a fixed constant, is equal to 2.9 times 10 to the minus 3. However, you don't need to remember this because when it comes to comparing the two different stars, for example, they both will have the constant the same. So you probably end up having an equation that's L max for 1 times the temperature of 1 is equal to the L max 2 times temperature of 2, since they are equal to the same constant. Now here to mention once again that the temperature here should be measured in Kelvin, where the wavelength should be measured in meters. So basically the unit would be meters Kelvin as a unit. Now, there is one thing that I wanted to mention here. Usually, you always have to change the temperature to Kelvin. However, you will notice that if the temperature is so small in degrees, since the Kelvin is so high in temperature, it won't really affect that value that much, but still use Kelvin. The power output of a star. Now, this is something that is based on Stefan's law. Now, before we go on to Stefan's law, just to remind you that the amount of energy a star radiates per second, or in other words, the power of a star in all directions, is called its luminosity. So this is basically the total power output of a star. So this is the luminosity. Now, Stefan's law states that luminosity of a star, which is a symbol L, is directly proportional to the surface area and is also directly proportional to the fourth power of its absolute temperature. Once again, this is in Kelvin. So the equation comes up to be luminosity is equal to 4 pi r squared times the Boltzmann constant times the temperature to the power of 4. This is the surface area of a sphere. So we can see that it's directly proportional to the radius squared of a star. Well, the distance from the star as well. Sigma, this is a Greek letter. Sigma is Stefan's Boltzmann constant. So this is luminosity. Sorry. Remember, since it's the total power output of a star, then it's measured in watts. This is the radius of the star in meters. This is Boltzmann constant. Stefan's constant. The values given to you is actually 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the minus 4. And then you have the surface temperature of the star. In Kelvin. So basically these are the two rules. So we're going to look at an example where both laws need to be combined to figure out the answer. Here it says the peak wavelength, so meaning the L max of radiation emitted by our sun is about 500 nanometers. So we write that down. Its surface temperature is 5,800 Kelvin, and its luminosity is, so this is all for the sun. And the luminosity is 3.85 times 10 to the 26 watts. The peak wavelength emitted by a nearby star with a luminosity 10 times that of our sun. So we'll write this down as the luminosity of another star, which is 10 times that of our sun. So that will be 3.85 times 10 to the 26 times 10, since it's 10 times more. And the peak wavelength for that is 310 nanometers. Show that the radius of the star, of this star, is approximately 840,000 kilometers. So I know that if I have the luminosity, which is directly proportional to the temperature to the power of 4. And I also know that it's directly proportional to the radius squared. Since I already have I need to show the radius. I do have the luminosity, so luminosity is equal to 4 pi r squared sigma for Stefan's constant t to the power 4. So this is a constant. I have the luminosity of the star that I need to find its radius, so I need to find radius, but I do not have the temperature of that star. But since I already do have the wavelength and temperature of our sun, and I know that that should be equal to a constant, so I know that L max times the temperature is equal to a constant, then so will the maximum wavelength of the other star and its temperature be the same. I'm just using a circle as a star just to differentiate between the sun and the other stars' temperatures and wavelengths. So I can multiply the first two values I wrote at the top. Well, yeah, 500 times 10 to the minus 9 times the 5,800 Kelvin for the sun, which should be equal to the wavelength times the temperature of the other star. So I know I can divide, if I want the temperature of the other star, I can divide both sides by the wavelength of the other star, which will be 310 times 10 to the minus 9. This and this cancel. So you will get the temperature to be 9,355 Kelvin. And then now you can put use this equation, rearrange it for R. So that will be R is equal to luminosity divided by 4 pi sigma t to the 4, and then you square root that. Then you simply put the values in of the luminosity of the new star. 3.85 times 10 to the 27, since it's times 10. You divide that by 4 pi, the sigma, which is 5.67, times the temperature to the power of 4. And you will get an answer of 8.399 times 10 to the 8 meters, which is about 8.4 times 10 to the 8 meters. And we know that kilo is 10 to the 3, so that will be 8.4 times 10 to the 5 kilometers, which is 803 kilometers, just like the, oh, sorry, I missed 10, just like the question asked. Okay, so going back to the learning objectives, we have looked at Wien's displacement law and what it means. It has to do with the peak wavelength and the surface temperature. We also looked at Stefan's law and how we can use the two to figure out the radius of a star.